So let us just revisit the meaning of position and displacement graphs. We said in a previous lesson that there are three things we always look for with every graph. We have our y values and our x values. And what we always look for first is to see what we can read off the graph. The second thing is, what does the gradient tell us? And the third thing is, what does the area tell us? Reading is just what the axes are. The gradient is dividing the axes. And the area is multiplying the axes. So in the case of our motion graphs, our position and displacement graphs, we can have x or we can have delta x, and we'll consider each one. What we can read from a position time graph is we can read position and time. The gradient is given as delta y over delta x, which is delta x over delta t. The x-axis is position given as x, and the x-axis is time, delta t. Now, if we then look at the units of this, delta x is in meters and time is in seconds. So we end up with meters per second. So the gradient in this case is the velocity. The gradient is the velocity, meters per second. And that is true of both the position time graph and the displacement time graph. Next, and lastly, to look at the area is a little more complicated on this graph. Simply put, we're going to multiply the axes. So in this case, we will have, let's say, x, position, times time. Now, if we look at the units of this, we have meters, and time is seconds. So the units are meter seconds. That isn't any quantity we recognize. So what we say is the area has no meaning. So in a position displacement graphs, we can read the position or the displacement in time. The gradient's the velocity, and the area has no meaning to us. We need to consider always every case, looking at the multiplication, the division, and the dimensional analysis to see if the units make sense. So if the gradient is the velocity, what do we do when we have a graph that is a curve? What do we do if the graph is a curve? Let's suppose it's a curve like a parabola. What we imagine is that we take a small segment like this and blow it up into a very large window. When we blow that curve up, it will look straighter. Just as the Earth is a sphere and has a curved surface, at our scale, when we blow it up and look at it at a human scale, the Earth's surface looks flat. Well, the same thing is true of all curves. So we imagine looking at the curve blown up to a large degree. What we can see now is that if we take this orange interval here, this is delta t, the amount of time. Now, remember, if we had our gradient, that's delta y over delta x, which is delta x over delta t. Again, coincidentally, the same x's, but the change in position over the change in time. Well, what we're doing by looking at a small interval is making delta t, the time interval, very, very small. And as we make the time interval very, very small, the curve begins to look closer and more closely like a straight line. So when delta t is small, we can do delta x over delta t. The problem is that increases error because we lose significant digits and so forth. To solve this problem, a whole field of mathematics, the calculus, was invented by Leibniz and Newton at approximately the same time to solve this, and you will learn about this in SL and HL math. However, the simplest answer to this question about how do we find then the gradient or the speed when we have this position time graph is we look to the tangent. So if we wanted at a particular time, this time, what we want to construct is a tangent at that point. Tangent being a point that touches the curve in only one spot. And now you can see we have this straight line, and we can obtain delta y and delta x values from which we can calculate the gradient. So the answer to what do we do when the graph is actually a curve is we try to envision over small delta t's that we will get an accurate value when we get the gradient. How do we get that gradient? We do our best to draw a tangent at that point, and once we have drawn that tangent, we then can get delta y, delta x values from that line that is drawn.